We are going to talk about section 11.4. We're going to look at graphing polar equations, and then we are also going to look at finding slopes of polar equations. So to graph them, one of the things we're going to be concerned about is their symmetry. Are they symmetrical about the x-axis? Are they symmetrical about the y-axis? Or are they symmetrical about the origin? Symmetrical about the origin is like a rotational symmetry, that if we would turn the figure or the graph around 180 degrees, would it be the same if we would turn it upside down? So A there, as we think about being symmetrical about the x-axis, we should end up with a point matching both above and below the x-axis. And then symmetrical about the y-axis, likewise we could like fold it closed like a book and we would find the match there. And then symmetrical about the origin is turning it around. And so it kind of looks like a diagonal symmetry in this, but it's more like we're turning our paper upside down, and would it still be the same graph? And then this is our formula for the slope of a polar equation. It's like, whoa, right? So it says that we're going to take our derivative of our function times sine, the function times cosine, and divide it by the derivative times cosine minus the function times sine. I'm going to show you where this formula comes from, and to be honest, I don't have this formula memorized. I know where it comes from, and so then I can use it according to that. And so we're going to look at where it comes from and how to apply it that way. So the first thing we're going to do is actually look at some graphs. So to graph in Desmos, you can graph polar equations, and you don't need to do any special setting change or anything to graph a polar equation. So I can just type in R equals, and now it automatically knows that I'm talking about a polar equation. And I can say 1 minus cosine. And then for theta, you can either bring up the little keyboard down here and get a theta in there somewhere, I'm sure. Or you can just type in theta, that's how we spell theta, and it turns into the theta. And we can see the graph there. So as we look at this graph, we want to think about what kind of symmetries do we have. So x-axis symmetry is folding it closed like a book like this along our x-axis, and that looks like that should work. If I fold it on the x-axis, the top and the bottom halves of the curves are exactly the same. So it has x-axis symmetry. If I take it and fold it closed on my y-axis like this, that's not going to match up. So no y-axis symmetry. And if I went and I turned it upside down, it's going to be out in the other direction, so that doesn't work. So this one only has an x-axis folding symmetry. If you want to, in Desmos, you can, in your graph settings, change it actually to a polar graphing system where it puts in the different theta angle lines there as well, and then those circles are the different r values growing out from the center. I don't usually bother to do that. I just look at it on the XY plane. But you can, if that helps you, change it over to those R and theta graphing lines instead. So to graph, you just type in your R. You can change your theta range here. So if we made this only go until pi instead, it's only going to graph the top half. If we make it go until 2 pi, we get the whole thing. By changing the multiplier here with theta, that changes the speed of the graph as well. So that one actually turned into something totally different as well. Now, one thing about graphing in Desmos for polar equations is that they have to be in linear R form. So if I type in our next equation that we're going to graph is going to be R squared equals 4 cosine of theta. If I do that, oops, sorry about that. If I do that, I get this little like warning sign, and it says they must be in linear R. So I need to solve this equation for R by taking a square root. So R equals the square root of 4 cosine theta. And then remember, when we take a square root in algebra, we also get a negative So I get this negative square root of 4 cosine theta. And so this is actually both of these curves together. It's not one or the other. It is both of them are the graph because of that plus and minus. So then when we think about symmetries, do we have x-axis symmetry if we fold it closed like a book this way? Yes, the top and bottom halves are the same. If we fold it closed on y-axis, the left and the right halves are the same. And if we turn our paper upside down, it would look exactly the same. So this actually has all three symmetries in it. Okay, so that's how we put our equations into Desmos to graph them and how we can analyze the symmetries of the graphs. Okay, for slopes, I'm gonna pull up my whiteboard here. All right, that made me go again. Okay, so all right, so when I think about slope of polar equations, what I actually think about is it's maybe a couple steps, but this is how it was explained to me, and it helps me not have to memorize that formula with primes and sines and cosines and everything. So what we're going to do is use the conversion equations from polar to x's and y's. And so we said that x is equal to r cosine of theta. That was from looking at that right triangle graph and saying that cosine is adjacent over hypotenuse. Okay, so x is equal to r cosine of theta, and y is equal to r sine of theta. And if I have an x equation and a y equation, I kind of have parametric equations then, really, right? I have an x equals and a y equals equation. They're in terms of theta instead of in terms of t, like we usually see parametrics, but I mean, theta even starts with t, right? So these are essentially parametric equations. And then we learned earlier in this chapter that a derivative of a parametric is taking the derivative of the y and dividing it by the derivative of the x equations. So that's how we are, or how I approach these problems. Now, if you would just rather use that formula, that's what it's going to turn into for every one of these problems. It's just for me, I prefer to know where did that formula come from, because if I had to memorize that, I'm definitely mixing up cosines and sines and minuses and stuff like that. So let's say in this problem, our equation is -1 plus sine of theta. Okay, so what I'm going to do is I'm going to take this equation and I'm going to turn it into an x equation. So x is equal to r -1 plus sine of theta cosine theta. That's our conversion equation with x's and r's and thetas. X is equal to r cosine theta. So that's my x equation, right? And my y equation is going to be y is equal to r -1 plus sine of theta sine of theta. Okay, now I could distribute that through, but I'm actually not going to bother to. I'm just going to leave it right here. And now we're going to find dy dx, the derivative of this. So when I find dy dx, we're going to find the derivative of the y. Okay, so now, because I have that purple times blue, and I did the coloring on purpose to try to help us keep track of all of our parts and pieces here, because I have purple times blue, I have a times, I have a product, so we're going to need to use our product rule to take our derivative. So in our product rule, I'm going to go first, so -1 plus sine of theta, first, d second. The derivative of, and I'm working with the y one right now, right, because the top is dy, so looking at that y equation, first, d second. The derivative of sine is cosine. So now that it turned into the x, but that's a little bit coincidental here. This is the first part of the product rule, the derivative of that y. So looking at the y equation, product rule, first, purple, d second, derivative of blue, plus second, which is sine, d first, derivative of -1 is 0, derivative of sine is cosine, right? So that is the top of this thing. And then on the bottom now, dx, so we're gonna look at the x equation and do the same thing, do the product rule. So product rule there, first is the function. D second, the derivative of cosine is negative sine. I put that negative out in front so it doesn't look like I'm doing purple minus blue, or you could put parentheses around it and keep it a negative sign together with parentheses around it. I should put that negative out front. So that's the first D second, purple D blue, okay, plus second cosine, D first, the derivative of the purple now, the derivative of 0, or of -1 is 0, and the derivative of sine is cosine. And so this is our derivative. And if I actually, so what we end up having then is, I'm gonna kind of label these, where they came from. The purple is our function, okay, so that's our f of theta. And then we have a times a cosine. And then we have plus a sine times our derivative of our function, right? Because that purple cosine came from being the derivative of the purple. Okay, so on the top, we have function times cosine and added to the derivative of the function times the sine. On the bottom, we have minus the function times sine plus cosine times the derivative. Okay, so if we go back to the slides, this is where that formula comes from. The derivative times the sine. Now in mine, it was at the end instead of at the beginning, just because I do first d second, and I think they do second d first in their product rule, but it doesn't really matter. So the derivative times sine plus the function times cosine. And then on the bottom, my minus is out front. So I have minus function times sine plus derivative times cosine. So I end up with this formula every single time, but it just happens for me by thinking about it as a parametric, an xy, and doing a dy dx that way. Okay, so now this derivative is super messy. We could maybe clean it up a little bit by distributing, and maybe some nice trig identities would show up, perhaps. I don't know tons of my trig identities, but maybe we would end up with a sine squared plus cosine squared, except we won't in this one. So what you're going to do with it at this point, typically, is then you're going to be given an angle for which you would want to evaluate the slope. So let's say that we want to now evaluate dy dx, the slope, at theta equals 0. Okay, so we're going to plug in theta is 0 here. Hopefully, I don't know if I left enough room there. Right little, I guess. So now I'm going to plug in 0. So I got -1 plus sine of 0. Ooh, what is the sine of 0? So either think about your unit circle or think about your graph of sine. Sine of 0 is 0. So that first purple part just becomes -1. Maybe I should go back to my purple and blue, and we can see where all this stuff is coming from. So that first part just becomes -1 because sine of 0 is 0. Times cosine of 0. Cosine of 0 is 1. Plus sine of 0 is 0. And then times, it doesn't even really matter what the cosine of 0 is because I'm multiplying it times a 0. So sometimes if these are really messy, I don't even bother figuring it out because I already have a 0 times something. So it doesn't matter what happens here in the purple, is this whole part's going to end up being 0. But cosine of 0 is 1. Over, I have then a negative out front. Don't lose that negative. I lose it a lot. So I'm speaking from personal experience here. Watch out for that leading negative there. And then in the purple, we get -1. And then the sine of 0 is 0, plus the cosine of 0 is 1. And again, the cosine of 0 is 1. So what does this thing all become then? -1 on top and 1 on bottom, and it becomes -1. So the slope is -1. Right? And on your problems, it might ask you to do more than one. I believe it does ask you to do more than one theta value. So we plugged in 0. You could then plug in pi halves or plug in pi or pi fourths. You might need to use some other special trig angles. But then let's take a look at what this is showing us on the graph. So our function is 1 minus sine of theta. So I'm going to turn those off, and if I do r equals 1 minus sine theta, this is our graph. And what we found was, what is the slope at 0? So our 0 angle line, if I switch over to our polar coordinate system, this is our 0 theta line right here. What is the slope at that line? That slope is -1. And that looks accurate to this graph, that if we drew in a tangent line right here on this 0 angle line, it would have a slope of -1. Okay, so that's what we're doing here when we're finding our slope. We're finding a change in y over change in x, but according to our r and theta graph. So at our 0 theta line, what is our change in y over change in x? Slope of -1 at that point looks accurate. So by looking at the graph, it can also help you judge your answers and make sure, especially, losing a negative or something like that. If we had actually thought our answer was +1, then we come in and look and go, well, that doesn't look like a +1 slope to me. Maybe I missed a negative in there or something. It actually looks closer to a -1 slope. It could also help you kind of make a guesstimate before you even do the work. Okay? So in this lesson, we looked at how to use Desmos to graph polar functions, how to analyze their symmetries, and then how to find the slope of a polar equation. So let me know what questions you have about this as you get to working on your assignment. I'm happy to help you with those, and we'll be back soon with lesson 5, which is going to finish out our study of polars and parametrics.